right, great. Well, my name is Sarah Rowley, and I'm happy to be joining you all from afar. Are you all able to hear me okay?
Yeah.
Okay, great. Well, I'm at the University of Notre Dame in the Department of Biological Sciences, and I'm part of a research group that's been looking at the water quality influences of the two-stage ditch. The other co-authors I've listed here are my advisor, Dr. Jen Tank, and Rob Davis, who is another grad student here. And I'll be presenting some of the data that he has collected, as well as some of my own. So just some background on the two-stage ditch. During rain events, basically that water is able to flow onto the floodplains, which slows the water velocity. And as a consequence, we've increased the water residence time, and we've also increased the stream surface area. And that means that we've got greater area over which that water can interact with the sediments, which results in greater time and space for biological and removal. Another thing that the two-stage ditch does is as it decreases water velocity, particles can settle out on the floodplain. That sort of can remove some of that sediment that's in transport, but also the fact that we've increased channel stability means we've decreased a source of sediments to the water column. And the result of this is a decrease in water column turbidity and also a decrease in sediment exports. And that's important on its own. We know that excess sediment can be a water quality problem downstream, but it also results in potential for increased light penetration. So that means that there's more light available for plants and algae in the stream, and that means that they can grow more rapidly and take up more nitrogen from the water column into their tissues as a result. Finally, there's more sediment deposition on the benches instead of in the channel, so we get some sediment sorting. In other words, some of those coarser substrates can be exposed, which can be improved habitat for bugs and fish. All right, so most of the data I'll be presenting today are from Shadow Ditch, which is in Kosciuszko County, Indiana. That's in the north central part of the state. It's about 10 miles west of Warsaw. And this ditch is fairly typical for any ditch in the region. It gets tile drain inputs. The watershed is largely row crop agriculture in a corn-soybean rotation. And historically, it's been dredged regularly to maintain that trapezoidal shape. So again, another picture right before the two-stage was constructed. After construction, you can get a pretty good idea of the dimensions of it. So the floodplains, or benches, were each 10 to 14 feet wide, and so the stream width triples during storms. So this is within that 3 times the main flow channel width. And apparently this is true with every single two-stage ditch project. We did have a flood shortly after construction. This one waited about 2 months. But there's a couple of things you can see. So the original channel is marked by these sort of grass tussocks here that were left intact during construction. And we were pleased to see that the channel stayed intact during this flood, even though there was no vegetation on those floodplains yet. I want to talk just briefly about our experimental design because it's important for understanding some of my figures later on. We use a before-after control impact design. And what we do in this design is we establish 2 reaches. There's an upstream control reach that we're not going to do anything to, and then a downstream reach where we will do the construction. So we monitor both of these reaches for 1 year so that we can understand sort of the baseline relationship between these 2 reaches. We then do the restoration or the construction, whatever you want to call it, on the downstream reach, and then we continue to monitor. And we're always comparing what's happening in the treatment to what's happening in the control, and that allows us to account for interannual variations. So we know, for example, that precipitation can strongly influence the nitrogen and sediment concentrations in these ditches, but because we're comparing it to an unmodified reach, we can account for those changes. Okay, so first I'm going to talk about nitrogen removal, and we're looking at 2 processes. The one I'm going to spend the most time on is denitrification. And denitrification is important because it's the conversion of dissolved nitrates in the water column to gaseous N. So it's a permanent removal. That nitrogen's turned into a gas in the atmosphere, totally out of the system. And this is a process that occurs naturally in sediments and soils. So we're not doing anything to change this natural process. What we're doing with the two-stage ditch is increasing the time and space over which this can occur. So we've got a wider ditch during floods, and so that water column nitrogen has more of an opportunity to interact with the denitrifying microbes in the sediments. The other process of N removal is what we call assimilatory uptake, which is plant uptake. And all the plants and the algae and also some microbes in the stream assimilate nitrogen into their tissues just as part of their natural growth. And this is not a permanent removal because these organisms will senesce and die at some point and then be decomposed. So the nitrogen will be returned to the water column eventually, but we call this sort of a buffering of the N export because this decomposition occurs slowly and that nitrogen is returned slowly instead of in a big pulse, which is what we often see in these systems. So first, we measure denitrification by taking samples across the reach. We sampled the two different sediment types in the reach, which were sand and fine benthic organic matter, or muck. And we measured denitrification in the lab. We found some patterns that are very similar to what we see in other streams. First of all, the rates do vary seasonally with surface water nitrate. When we compared the nitrate concentration in our in-shadow ditch and the denitrification rate with other studies, we see that we've got really high denitrification and really high nitrate. So there's a lot of potential in this system. The other thing we saw is that our bench denitrification rates, the green triangles here, were lower than the in-stream rates. But really what we're interested in is the total N removal at the scale of the reach. And so we calculated that by multiplying our rates, which are expressed per area, by the area of the ditch. And we partitioned this into bench removal, sand, and fine benthic organic matter removal. So here I'm just showing the in-stream removal, and there's a bit of a seasonal component to it. And also we see more removal in this mucky stuff because that's what most of the ditch was composed of. Now here I've added on the bench removal. And we saw on the previous slide that we had lower denitrification rates on those benches, but they still make a significant contribution to reach scale N removal because there's so much surface area in those benches. On average, we tripled the nitrogen removal with the two-stage ditch. And there's a bit of a range. When the benches are frozen solid, they're not doing a whole lot. But then on some dates, we had 12 times higher nitrogen removal with the two-stage ditch. We want to put this in context a little bit. So we're looking at how much is removed relative to the load. So the first thing we calculated was nitrogen load, which is more or less just the total amount of N that's exported. We have expressed here as kilograms per day. Should be similar. You could also express it as pounds per day or something like that. But what we see with nitrogen load are these seasonal patterns, which is pretty typical. So a lot of nitrogen is being exported in the spring, not as much in the summer and fall. So the next thing we looked at was nitrogen removal efficiency. So that's just the nitrogen removal that I showed in the previous slide divided by the nitrate load. And there's quite a range in this as well. First point is that we increased the nitrogen removal efficiency from 1% to 3%. So prior to putting in the two-stage ditch, that stream bottom was processing and removing 1% of the load. Now it's processing and removing 3% of the load. And there's some interesting points we can make here. So first, the highest nitrogen removal occurs when the load is lowest. Basically what happens in these streams is when there's a lot of nitrogen moving through the system, it gets saturated, and the biological removal capacity sort of tops out. It can't remove an infinite amount of nitrogen. But when the load is low, those denitrification rates are still fairly high. and they're able to remove much more of the load. So here in August of '08, we were removing about 15 to 16% of the load. So that tells us that if we can reduce some of the inputs to these ditches through managing the tile drains or managing the fertilizer on the field, we can probably attain additional N removal efficiency in these two-stage ditches.
Hey, Sarah, can I make one point really quick?
Sure.
Shadow ditch, at this point where the restoration was done, was, I believe, about 5 square miles. Is that right?
Yeah, I think that sounds right.
When she's talking, we're talking an entire watershed load, so 5 square miles worth of nitrate load was what was being treated by this small area of benches. And what the benches were, what percentage of the watershed area did they occupy? Something like 0.04% of the watershed area. So we're talking about a very small area treating, you know, it may look like the efficiencies were low, but we're talking about a very small area treating a very large area. So that, just hope that puts that in a little bit of context, that you don't get down on, only 3% or only 10% or 14%. And I think she'll address that a little bit in some further slides. So sorry to interrupt.
That's okay. I think that's a really good point. And the other point I want to make is that Shadow actually has high nitrate concentrations even for an agricultural stream. So for those of you who look at these numbers, it ranges from about 2 milligrams per liter to 11 milligrams per liter. And it's never been below 2 milligrams per liter. So that's a lot of nitrogen. So in some ways, Shadow is almost a worst-case scenario in the sense that it's already dealing with a lot of nitrates. And so potentially we could see greater efficiency in streams that were already getting lower N loads. So to sort of continue with what John was saying, you know, we're sort of asking this very small part of the watershed to treat an entire watershed load. And so we asked the question, what happens if we were to increase the length of the two-stage ditch? And John worked up these numbers for us. We had two scenarios based on what we had observed and measured in the field. 2008 was a dry year, where those benches had water on them for 29 days. We also had low denitrification rates in the floodplains. 2009, we saw the opposite, where we had water on the benches for over a third of the year, and we had higher bench denitrification rates. Now, this first line here is showing the estimated annual load reduction based on what was actually there. And then we scale up to if 50% of the ditch length was in two-stage ditch, or if 100% was in two-stage ditch. And it increases with length. So we get around 10% of the load removed when we've got the whole watershed in two-stage. So basically, the longer the two-stage, the more load reduction we achieve. My bullets are a little out of order, but that's okay. I also want to point out that this estimate is conservative, again, in part because we haven't accounted for the uptake by plants. This is uptake by denitrification only. So this is only the permanent N removal we're talking about here. And also the way we did this was we only included the floodplain contribution when they are inundated with surface water. So we know that they're denitrifying all year. They're taking up some of that groundwater nitrate and removing it. So probably they're doing a little bit more, but we wanted to be conservative. We didn't want to overestimate what we're saying these ditches are doing. And then the other point I wanted to make is that the importance of the bench contribution depends upon two things. One is the aerial denitrification rate, and the other is the amount of time those benches are inundated. So if we compare these 2 years, we see in 2008 we had low denitrification rates, and they weren't often flooded. We were removing just 21 kilograms of nitrogen per year, substantially less than what the stream was removing. But in 2009, we sort of had the opposite scenario where they were flooded a lot and we had high rates. And in this year, the bench contribution was similar to the in-stream contribution, even though we're only accounting for them when they're flooded. So sort of a design detail is that we want the benches to be constructed low enough that they do flood frequently so that they're doing something for water quality. Of course, if you go too low, you'll have problems as well, but finding sort of that height at which they'll flood regularly is important. All right, so in addition to studying shadow ditch, we also studied 5 other two-stage ditches in the tri-state area, and but all of those scaling up estimates that we made were just with shadow ditch. We found when we studied these other ditches that the end removal capacity of the floodplains increased with age. So over here, this is what shadow ditch was averaging for denitrification rates. Here's the mean of all the in-stream denitrification rates. And then here's what's happening on some of those older systems. So this is just about a 6-time increase in denitrification rate on those older ditches. And we think this has to do with the soil quality. So over time, the soil organic matter content increases. And this is probably due to, as Dan was talking about, the deposition of those fine sediments. Also, the establishment of vegetation can add organic matter to those soils. So again, those estimates we're making with shadow are conservative, and we do expect denitrification rates to go up over time. Another interesting thing I'm going to show is a little pilot study that we did last summer. So this picture here is sort of an aerial schematic of a two-stage ditch. So this is the stream in blue running down the middle. This would be the bench area here, and this is a tile drain outlet. And in some of these systems, the tile drains are allowed to just flow onto the benches, and they kind of meander their way across the bench to the stream. And we were wondering what happens to the nitrate in that tile drain flow path. So we know that tile drains are a source of highly concentrated nitrate. And so we looked at that, and here's the result. We looked at 4 different tile drains at one site. This is at Creel Ditch, which is one of the sites that John showed in his introduction. And we see a 6 to 19% decrease in tile water nitrate as it flows across the bench. Now, the concentration right at the outlets, I think, ranged from I think 4 to 18 milligrams per liter nitrate. So that's a lot of nitrate coming out of those tile drains. And a 6 to 19% decrease is fairly substantial when you're talking about that much nitrate. So this summer, Rob, the other co-author on this talk, has done some more measurements of this at other sites to see if this pattern sort of holds up across sites. But it looks like so far that if we can retain tile drain flow on those benches, we can reduce end inputs to the ditch. So, there are various ways to do that. In some cases, you can just let it spill on the bench. But as it's moving across the bench, it is denitrifying. So that's great. And another design detail is that the presence of riprap could inhibit this process. So riprap is, of course, huge rocks. There's not a lot of organic matter associated with them. There's not a lot of surface area for microbes. And so there's not a lot of denitrification that can occur on the riprap. So there are ways to design them so that maybe there's a little riprap right at the outlet, but after that they're allowed to flow across the bench. You'll get additional water quality benefits with that. All right, I'm going to move on to a slightly different topic, talking about turbidity and total suspended solids. So first, I'll just tell you a little bit about how we measure these things. Turbidity is fairly easy to measure. We have these data sondes, and these data sondes are equipped with various sensors, including this self-cleaning turbidity sensor. And they can just be put in the stream and programmed to record measure and record turbidity. So we have these sondes that are measuring turbidity every 30 minutes in the treatment and control reach. We're also really interested in sediment export, but we can't measure sediment export continuously. You actually need to take samples back to the lab to do that. So what we can do is create a relationship between this turbidity, which we have continuously, and total suspended solids, or sediment, which we have from samples we've taken out at the ditch. And then we can use that relationship to get sediment export continuously. So to get our TSS, we use these automatic water samplers. So at Shadow Ditch, we found that the two-stage did reduce sediment export. And again, we're estimating sediment with this turbidity TSS relationship. This is just in the first year after construction. So prior to construction, the control reach had less sediment export than the treatment reach. After construction, the opposite was true, where we had less export from the treatment reach. It's a 20% decrease in export. And this, of course, is useful in itself, but there's also some implications for phosphorus export. We know that phosphorus is often sorbed to those fine particles. So if they are settling out, it could mean a reduction in phosphorus as well. And Rob has been collecting samples to examine whether this is true, but those data aren't worked up yet. So I hope we'll find that there is a phosphorus effect as well, but we don't know for sure yet. So that was sediment export. That's the only site for which we have worked up the sediment data, but we have turbidity data for a number of years in a number of sites. So here's just Shadow Ditch. This graph is showing the reduction in turbidity. So in 2008, so the mean difference between the two, between the treatment and control reach. So in 2008, that's what I showed in the previous slide. We have a reduction, but it's not all that dramatic. And then in 2009 and 2010, we had an even greater reduction in turbidity. And we think what's happening is that the benches take some time to vegetate. And so in 2010, they finally vegetated fully, and they slow down the water even more than just a bare soil bench. And so we think that's responsible for reducing the turbidity. So it certainly appears to be self-maintaining, and its efficacy did improve over time. We don't expect it to, continue to improve forever, but certainly it improved over the first 3 years after construction, and we expect that it'll sort of continue to be at this level in following years. So in addition to Shadow, we've looked at turbidity in 5 two-stage ditches, and we see very similar patterns. So for this study, we separated out our turbidity based on discharge. So we've got base flow, storm flow that didn't inundate the benches, and then floods that inundate the benches. And control reach in gray, the two-stage reach in maroon. And at 4 out of 5 of these sites, turbidity decreased during storms. The exception was Powers Ditch, where turbidity actually increased in the two-stage, but this is because it was not constructed properly. The project sort of ran out of funds before it could be completed, and so the benches just slumped right into the stream. So, like any management practice, it really has to be constructed properly in order to work properly. So we're encouraged by this decrease in turbidity, but we're going to link it back to N export. As I mentioned at the beginning of the talk, we hypothesized that if we decrease in-stream turbidity, we might increase in-stream plant production. And indeed, that is what we found. So we're going back to Shadow Ditch here, and we have plant production here comparing pre-restoration and post-restoration, and we see an increase. And that increase is correlated with a decrease in turbidity. So the lower the turbidity, the higher the primary production, basically. And over here, after the restoration, we saw some of the lowest turbidity we've seen in the ditch, and we saw some of the highest plant production we've seen in the ditch. So basically what happens again, lower turbidity, increased light penetration results in higher plant growth, which is what we see here. And as those plants grow, they take up nitrogen. So we're increasing N removal. We're hoping to scale this up to an N removal number, which we don't have yet. But certainly we know that there's additional N uptake occurring by the plants as a result of the restoration. I just want to quickly talk about habitat. We don't have a ton of data on this, but what we do have, I think, is very interesting. So we regularly at Shadow Ditch, we characterize the sediment in the ditch. So prior to construction, we had, as I mentioned earlier, this fine benthic organic matter, this really fine mucky stuff, and we had sand. Now, after the restoration, indicated by this red line, we started to see other substrates. We started to see gravel and cobble and clay. And this is potentially good habitat for fish and bugs. Another grad student in a different lab here started looking at the fish and bug populations in these ditches. So we'll see if this change in sediment equates to a change in the biological community as well. Just to recap everything I've said, I've presented a lot of data. The two-stage increases nitrogen removal. At Shadow, it tripled the permanent N removal via denitrification. Also increases the N removal efficiency, and we can further increase N removal efficiency by increasing the length of the two-stage ditch. I also want to point out that we've been conservative with our N removal estimates for a few reasons. First, we were using bench denitrification rates from early on. It appears that they do increase with age. Also, our estimates come from Shadow Ditch, which is has exceptionally high nitrate compared to other ag streams. And we also haven't put in that plant uptake numbers into our total removal estimates. But I also want to point out that even though our estimates are conservative, we don't think that the two-stage ditch is going to solve all of our water quality problems. We don't think that's realistic. And so the two-stage ditch, as we saw, the N removal efficiency goes up at those lower loads. So if we compare it with other management strategies, we're likely to get even better nitrogen removal and sediment removal as well. Again, it reduces turbidity and sediment export. It looks like it improves benthic habitat with those coarser substrates. And finally, I just wanted to say the simple summation of my talk is that the two-stage ditch reduces sediment and nitrogen export. It also appears to be self-maintaining, and its performance does seem to improve over time. Finally, I just want to throw some acknowledgments up here. They had a lot of help collecting these data and funding for this project. And I also want to point out the denitrification data that I presented for Shadow Ditch has been accepted for publication in Ecological Applications. It's a peer-reviewed scientific journal. And so if you're interested in more of the details, there's some additional calculations in there and so forth. The preprint is now available for download at this website. Basically, this website will give you a whole list of preprint articles available for this journal, so just scroll down until you find this one, and you can download it. Also, if you have any additional questions, feel free to contact me at, here's my email address here, and I'd be happy to discuss this further with anyone. And then with that, I think I could probably take a few questions if there's time.
I will post that. Or, yeah, I'll get that by the end of the day.
Any other? Dan?
Sorry if I missed it, but the 600-meter reach here, how many meters of ditch are upstream from it? We're talking about the size of the watershed, but specifically, how much ditch is upstream?
Of the treatment station.
How many? What was it? What were the number of channel meters upstream of the reach?
Ooh, well, we could do, I think it's on this slide. Let me go back.
I think it was something like 10 kilometers. I believe 600 meters was 7, was it 7%?
Yeah. So here it is right here. There's 8.4 kilometers upstream.
As long as you're on that slide, how can it be that the 100% is only
answer that?
Yeah, I think you probably will be a bit more accurate than I will, so I'll let you answer it.
Okay. Right. So that 8%, we have the whole 8.4 kilometers. So before the restoration, the trapezoidal bed was doing some amount of water quality improvement. There was some denitrification occurring. So that 0.6% is the 8.4 kilometers.
I don't think 0.6.
Kilometers.
Kilometers, sorry.
I'm looking at the 8.9% versus 10%.
Right. So actually, the benefit of the ditches in this case was the difference between 10 and 8.9. So the benches we've only calculated denitrification on the benches on those 29 days. And although we know they measured denitrification, and it was occurring year-round. So was it pretty much every time you went out and measured it, there was some amount of denitrification occurring? So there's
Yes.
ground coming through there. There's exchange of, even when it's not out on the bench, when it's not inundated, there's exchanges of water from upland to the channel through groundwater flow, and vice versa from the channels back. So they measured denitrification even when they weren't saturated. So that's why she said they're very conservative. So originally there's the 600 meters of two-stage plus the entire drainage network of the ditch bed. So the year that it was out for 130 days, it increased the nitrate uptake by 4.4%. So it was, this would be a case for perhaps building lower benches, or if you want to say you may want to build a self-form stream, because there's more contact going on through organic matter. So what we didn't want to do is we didn't want to say that we wanted to show the difference. There was some benefit of the system that was there before, and then there's some benefit of the system if we modify it to the two-stage form. So by presenting both numbers, you can see what the benefit of the bench was. And like I said, these are very conservative numbers by only including the days that the water was out on top of the benches. Part of our research going forward would be trying to see, what are the benefits of the bench when the water is not inundating, the benches over out on top. So, they may seem small, but, really it's a high nitrate, larger.
Well, no, all I'm saying is the difference between 8.9 and 10 is what seems small. So the 8.9 doesn't seem small.
Well, in that particular year.
It should have gone up, but so that's what's distressing.
But that
John,
was the number of days they weren't inundated for very much, and we're not, like I said, we're not including all of the denitrification of groundwater during this. We only included it when it was out. So that's 29 days versus perhaps beneficial things going on 300 or 365 days a year.
But John,
Yeah.
is some of this because the surface area in bench is going to decrease as you move upstream because the channel decreases?
Say that one more time.
Is some of this, so it's not increasing at a one-to-one rate basically as you increase the length of the two-stage. Is that because the surface area in bench decreases as you move upstream into a smaller channel?
No, on that one I assumed it was uniform throughout because that was a pretty standard bottom width. So.
And then Dan, you had a comment?
You're saying that if I do 600 meters of project, I get almost 9% benefit. And if I do another 8 kilometers of project, I extend that project out another 8 kilometers, all I do is get 1% more.
In that particular year, the method that we used, only including the days that it was inundated, that's why we say they're conservative. In that particular year, using the median denitrification rate, that was the benefit.
That won't be compelling argument.
So the number of days when it increased the contact, this was a high nitrate stream, and the surface area of that is very, very small. It was
But you're explaining why 10% isn't smaller. Isn't larger. But you're saying why is the difference between 8.9 and 10 smaller? And all the things that you're explaining don't have anything to do with that difference. I mean, so what it is the actual benches hardly had any effect in 2009, and that 8.9 was mostly in the stream. So if there was another column above it, which was no two-stage at all, it would still be 8.5 or something
Right,
like
exactly.
that.
So perhaps that was another line.
That's the confusing. So we won't use that in extensive.
Okay, there we go. But, yeah, the benefit of benches is the difference between those two numbers.
Yeah.
But,
0 is under 8.1, 8.6 something if you're making.
right, yeah, so we wanted to include what the existing benefit was before the modification occurred. So that's included when only 600 kilometers of the drainage network, and you know what, it explained it very clearly in the text. So, yeah, I think it's worth it. Is that,
This point might have already been made, but I think one of the points that you're trying to get at, maybe what everybody else is getting at, that in 2009, where there was more inundated days, we got not quite double, but the difference between treating 0.6 kilometers and 8.4 kilometers is substantial.
right.
So the better number to spell it would be in 2009, for example, you had a 90% increase in the amount of load study.
Well, as long as we're talking about what elements are used by one issues, but I don't think we need to talk about this percentage at all. That's my thing. Because everybody knows there's a whole bunch of nitrate, and anything we can do to get rid of some number of kilograms is great. We don't need to say it's 1%. That's what I was trying to get to the number. It's some number of hundreds of kilograms. So let's just say it's hundreds of kilograms. Because that's all the load reductions for like TMDLs are not in a percent, they're in an amount of kilograms. So I would say, it's like apologizing if these are conservative because shadow ditch is so high. That only makes the percentage lower. If we just talk about actual amounts, it's got to be higher when it's a higher stream. So I would stress that in that register for you too, right? We're going to get rid of kilograms of things.
And that's why you might argue that you would really want to put these in the places where the efficiency is lowest, because that's where the highest loads are going in, and they're doing the most
I
work.
probably wouldn't use the word efficiency with
Yeah.
that. I don't find it a helpful word.
Just one other point about the hoteling thing. I mean, we're all interested, many of us are interested in water quality improvement or making the practices for irrigation on the landscape more sustainable or whatever. And there are multiple methods we have for doing that, multiple practices. And so I do think it's important for us to look at the benefit per dollar.
Yes, that's the fact.
Right.
Yes,
So
that would be the efficiency I would use.
And so no matter, whether we're talking pounds of nitrogen removed or, whatever, but I do think it's important to consider how two-stage ditches compare to other methods of nitrogen removal, so we're using our money wisely and advocating
Yeah.
for practices that
And a lot of what we do is try and build tools to do exactly that. Like, what's the benefit of a modification going to be in terms of water quality improvement, number of pounds, but also what is the cost? Anytime you make a decision to put one in, it ought to be because there's better cost-benefit analysis. And we build a lot of tools like that. I have seen Wayne Skaggs and his group did look at nitrate cost per removal, cost per pound, and I just did some quick calculations, and I think a lot of times the two-stage ditch would be very competitive with some of the other options out there. Other times not. That's a good way. I just want to make a point, in a journal article, which this is coming from, I don't know that we're necessarily selling anything. We're reporting what it was, and that's a common in that type of text, how things are reported. So yeah, I agree when
Well, I mean, I think it is, because even scientifically, is it pounds per, you need the total pounds in the denominator, and I guess I would argue that you don't, you're assuming that efficiency does have pounds removed per pounds that were originally there, but you could also just talk about efficiency as pounds removed, per dollar, whatever.
yeah.
So yes, you certainly have that with your interest.
Yeah, what?
This is what I think, it's a comment to many
move on to our next.
Thank you, Sarah.
Yep, thank you.